Hello everyone, I am Ravneet Sani, lecturer PG Department of Chemistry, Kanya Mahavidyalaya Jalandhar. From last few years, I have been working with computation tools and software. So based on these tools and computation chemistry, I am presenting my poster on computation analysis of interactions between curcumin and the target main protease Mpro of SARS-CoV-2 in the two-day national conference on COVID-19 pandemic, emerging challenges and future strategies. I think the major challenge in front of us these days is to develop an effective drug against coronavirus. This COVID 19 outbreak was first reported from Wuhan, China in December 2019, and till date, this corona infection has affected so many people globally. This COVID 19 has squeezed the global economy. The present scenario manifested higher demand for safe and effective drug to control this coronavirus infection and to improve the lifespan of the people who are suffering from this corona infection. But the effective drug against corona infection, they are still under exploration, they are still under experimentation. Moreover, the process of novel drug discovery is quite time consuming, risky, and costly. So I think CDD, that is computational drug designing, is one of the most effective method to achieve this goal.
In this poster, I have presented the docking between the ligand and the protein. So it's a sort of complex formation between the ligand and the protein, and the docking poses were received, and I have selected the most stable one on the basis of binding energy as well as the interactions between the protein and the ligand. So the protein which I have selected for my docking was a 3D crystal structure of COVID-19 main protease in complex with an inhibitor N3, that is Mpro. The structure is also called Mpro. So the structure was downloaded from PDB, that is Protein Data Bank, with the PDB ID 6LU7, and the structure was downloaded in the PDB format. So after downloading the structure, this 3D structure, as you can see this green one, after downloading this structure, I have prepared that protein in the Discovery Studio software. So here you can see the sphere also. So in the preparation step, what I have done, I have added some polar hydrogen, removed some non-polar hydrogen, added some charges, and also I have selected the binding site for my ligand from the current selection, that is already binder ligand. The sphere here it shows the binding site for my ligand. Side by side, I also noted down the various attributes that I will need later on to run my file in the command prompt. So attributes like XYZ coordinates, the radius of the sphere, and moreover the question arises here that why I have choose this target, because Mpro is one of the key enzyme of coronavirus that plays a major role in the viral replication and transcription, so making it an effective drug target for the virus. So that's why I have chosen this structure. This is the image where you can see the various polar hydrogen that were added to the protein. So after preparing my protein, I saved that file in the PDBQT format. So after that, I chose my ligand for my docking, that was a curcumin. This is a structure of curcumin. So curcumin, produced by Curcuma longa plant, member of Gingiberaceae family, exhibit various antiviral properties. So it was also proved in various research papers that curcumin and its derivatives like gallium curcumin, copper curcumin, they inhibit the gene expression in HIV-1, HIV-2, influenza, herpes simplex virus type 1, and also it was proved that virus incubated with curcumin loses infectivity, as curcumin it interferes with the viral cell binding. So moreover, it is a natural product, so I think it is most suitable in terms of least side effect. So the structure of this curcumin, it was this ligand, it was downloaded from PubChem in SDF format, and it was converted to PDB format through an online converter. So and after downloading the structure, it was also prepared in the Autodoc software, like I have prepared my protein in the Discovery Studio, where I have added some charges and converted this ligand into the PDB QT format. So after preparing my ligand and protein, I have generated a config file in which I mentioned all the attributes, name of my prepared ligand, name of my prepared protein, how many times I want to run my docking process. So after successfully running my file in the command prompts by giving various commands, I have generated this log file. As you can see over here, that there are the 9 poses, and corresponding there is also the binding energy in kilocalories per mole. And these poses, they are together, so there is a need to split these poses into an individual pose. So for that I gave the Vina split xe command, and I split each pose, and I visualize individually each pose in AutoDock as well as in the PyMol, and visualize the various interactions that they have made with the ligand, that have made with the protein. So in this result, I have seen that the docking pose number third, it forms the most stable complex with the least binding energy, as well as in this, you can see over here in the 2D structure, there are the 3 hydrogen bonds that the ligand made with the protein. So these hydrogen bonds, they were with the amino acid glucine 166, serine 144, cysteine 145, as also this pink one, it is a pi-pi interaction with the amino acid H1S41. So results clearly reveal that my ligand curcumin, it successfully bind with the protein. And moreover, results reveals that the use of natural products like curcumin can lead to the rapid discovery of drug leads with clinical potential in response to new infectious diseases. So at last, I would like to thank KMV for providing me this opportunity to present this poster in this 2-day e-national conference on COVID-19 pandemic. Thank you so much.